Welcome again. I will now explain what happens when you have an unstable pole placement controller. We will study the impact of this controller on closed loop response. We will propose an improved controller configuration. I will show some Scilab code and results. Let's recall the 2 DOF controller as given here. We have expressions for TC, RC and SC. We put those values in these boxes. We also obtained the closed loop transfer function given as capital T. So when I simplify this, I get this expression. Here I have cancelled the good factors. Now let me multiply both numerator and denominator by ABR1. I get this expression. I have written this R1 in blue and we are going to cancel this. And let us see what happens when R1 has its 0 outside the unit circle. That is when the controller itself is unstable. So supposing I cancel this, I get this expression, which is what we did in the previous video, and this was equal to BR by phi CL. This is our reference model as we had before. As I mentioned earlier, notice the cancellation of R1. So I have cooked up an example to illustrate this. Here is the plant. The rise time is 10 samples, overshoot is 0.1, epsilon is 0.1, and you find that BB to be this whole thing 1 minus 3Z inverse, and BG is of course 1. What about the denominator? What about AB? AB is once again this whole thing, which I can multiply as follows. So what happens to AG? AG is equal to 1. So this is a specific example I have put together, and for this, for the desired rise time and overshoot condition, I get this phi CL. Then I solve Aryabhata's identity. I get S1 and R1 as follows. Notice that this R1 has its 0 outside the unit circle, and as a result this controller is unstable. Okay, it is an unstable controller. So I have given the Scilab code for this. It is called unstb.sce. It also uses desired, pp basic and so on. You have already seen this earlier, and after that I invoke this xcos function called basic underscore disk by running this Scilab code in the console. It loads, it opens, assigns values, and it also simulates. You do not have to press any button once again. And here is the screenshot of the Scilab code. It is called basic underscore disk dot xcos. This is the xcos code that you get. This is what you have to use. Using the function explained in the previous slide, this is automatically opened and simulated. And what response do you get? It is shown in the next slide. As feared, you can see that the plant output becomes infinite. Of course, you have to wait for a long time. The values build up, eventually blow up. You can see the value to be 10 to the power 12 here. And here is the corresponding control effort, that is also very large. So as we expected, we got instability because of the cancellation of R1, and this R1 had its 0 outside the unit circle. So what do? First of all, I would want you to verify this. I would want you to reproduce this Scilab simulation. So let us suppose that we take RC equals BG_R1 inside the loop. So there is no issue of R1 appearing from here and cancelling something that appears in the denominator. So I have taken this RC inside What is RC? This is BGR1. Where does it appear? It appears in the denominator here, it also appears in the denominator here. So I have taken it inside. Remember, however, we are not talking about calculating the controller at all. Whatever controller that we calculated earlier is okay. It is just that the way we have simulated is not okay. So I am proposing that we have RC inside the loop. So we can verify that we get stable response. As I mentioned earlier, there is no need to compute the controller at all. Here is the XCOS code I have used, stb_disk.xcos, and here is the screenshot of that. Compared to the previous XCOS code, now we have an extra block. In fact, I would want you to go back and verify that this is indeed an extra block that we have now. When I simulate it, lo and behold, I have a bounded value for all values. I am simulating up to 1000 here also. Here is the corresponding control effort. So this brings us to the end of this presentation. In this lecture, we started with an unstable controller, and we suggested that the basic control design that we used was okay, but the way we simulated was not okay, the way we implemented it through XCOS was not okay. We should have the unstable part R1 present in only one location. It should not be present in two locations, which resulted in cancellation. I hope that you will reproduce all the Scilab simulations and verify all the results. Thanks for joining. Goodbye.